We have learned that to calculate the arc length between 2 points on a plane curve or space curve, we evaluate a definite integral whose limits are the values of the parameter t equals a and t equals b corresponding to those points. In general, the arc length is not directly related to the parameter t used to define the function. However, for some applications, it is useful to redefine the vector-valued function using the arc length s as the parameter. This is referred to as an arc length parameterization of the function. In order to obtain an arc length parameterization, we will first need to define an arc length function. This will give us the arc length as a function of the parameter t for any t greater than its initial value a. Once this integral is evaluated for a given function r, we will have a relationship between the arc length s and the parameter t. We then solve this relationship for t and substitute for t in the original function to rewrite the vector-valued function in terms of s, the arc length parameter. The nice thing about an arc length parameterization is that when a vector-valued function is defined this way, the distance along the curve starting from s equals 0 is now equal to the parameter s. Alternately, if we have a target arc length in mind, we can easily find the point located that distance from the point at s equals 0 using this parameterization. It is also important to note that if the magnitude of the derivative of the function defined in terms of the original parameter t is equal to 1 for all t greater than or equal to a, then the function defined in terms of the parameter t is already an arc length parameterization, and t is the arc length starting from the point a. Let's try an example. You are asked to find the arc length parameterization for a curve for t greater than or equal to 0. The first step is to find the arc length function s of t. This will give us the relationship between s and t that we need. We find the definite integral from 0 to t of the magnitude of the derivative of the given curve. We obtain the result that s of t is equal to the square root of 14 times t. This is the relationship we were after. We solved this relationship for t to find that t is equal to the arc length s divided by the square root of 14. Lastly, we substitute this expression for t in the original r of t and obtain the arc length parameterization r of s. Note that this parameterization of the curve will allow us to easily locate the point that is located s units from the point at s equals 0, a very useful application.